What's up, physics? Welcome back to the Dirt Bike Shed. Today we're going to keep talking about centripetal acceleration, except for on a bigger scale, okay? I've got two basketballs and a soccer ball over here, and I'm going to throw them that way, and I just want you to watch how they fly. And I know, I already know how they fly. Yes, they fly in a parabola, but just take a look, okay? And I'm going to throw them with three different velocities, okay? All right, here we go. Now, you're probably thinking, well, that was stupid. I've seen someone throw a ball before. But notice the difference between the three throws. When I needed to get the ball to go further, I had to throw it harder. And I also gave it a little more of an angle. Yes, we've already studied trajectory, but Isaac Newton started thinking about throwing things across the earth really quickly. And then he had an idea about it that may surprise you. This little connection we're going to make to centripetal acceleration. Let's go check it out. So Newton's thinking about this, and in Isaac Newton's day, when there was also a pandemic, right? They had cannons. I'm going to draw like a old-fashioned, very short cannon here, okay? And we'll shade it. And we've got a ha-ha. Okay. And the cannon shot a cannonball, and this will be like a real short one on the deck of a ship or something, right? Okay, and the cannon shot a cannonball, and depending on, here's some water. Now, depending on the velocity, right, the initial velocity, and you're like, Mr. Perkins, we've already studied this. Well, hold your freaking horses for a second. He got to thinking, hey, what if I had a really powerful cannon and I was trying to hit a target very far away? Then I would shoot this thing up in the air, and if I could shoot it hard enough, I could get it to land somewhere else on the earth. And now we have intercontinental ballistic missiles that do that. But this, for him, it was just a thought process. And yes, an intercontinental ballistic missile has rocket propellant and stuff, so it's not a true, just straight up projectile. But anyway, then he was thinking, hey, you know, if I shot it hard enough, I could hit myself. And then he took it to the next level. He's like, well, if you shot it hard enough, couldn't you just to get it to go around the world and keep going? And do you know what that would be called? That would be called orbit. So orbit is really a centripetal acceleration. And the radius of orbit is just really long. Check out these numbers. Check out those numbers. The radius of the Earth is 6.36 times 10 to the 6 meters. Now that is 6,360 kilometers, right? And this is the mass of the Earth, which shouldn't matter to you yet. The mass of the Earth because we've been talking about centripetal acceleration and centripetal force. We've been talking about the object that is actually rotating, right? And this mass of the Earth, we haven't talked about before. Well, guess what? The mass on the inside of the circle in space is what creates the rest of the circle around it. Okay? The Earth, being in outer space, warps space and time itself. I know that sounds crazy, but take a look at this. Here is a sheet on a bed, right? Here's a bed, okay? Boom. All right, now, if we put a bowling ball on this bed, wouldn't it dent the mattress? Wouldn't the mattress now be shaped like this? Well, that's pretty much what massive objects do to space. Massive objects warp space and time. I know that sounds crazy. We're not going to talk too much about time. Warp space and time around them. So when we're looking at this, outer space is now shaped like this. Now, I've only drawn this in 2 dimensions, and there are many, many more dimensions than 3 that you're used to dealing with. But we're just going to look at this 2-dimensionally from the side. If the Earth, I'll make it green now, if the Earth and its mass are influencing space-time, then we can think about objects in centripetal acceleration as going around and around this funnel, okay? Now, if you don't know what I'm talking about, imagine that you have a quarter and you put it on one of those machines. It's not a machine. Let me show you what I'm talking about. This is what I'm talking about. Can you see the coin going around there? Well, this down here, this is where the Earth is. This massive spot here in the middle, right? Let me draw the Earth on here. This is where the Earth would be, right? In the middle of this spiral. And now you can see that space and time are warped down towards the Earth, okay? And that for something to be going in a circle here, they're just riding around this warped space-time. So if we go back and we play the coins rolling, these coins are orbiting. And orbit is what that's called. So we're going to talk about centripetal acceleration around a planet. And the centripetal acceleration around a planet is due to this force. And that force is the force of gravity. Okay? That's the force of gravity. There's a formula. The force of gravity equals capital G, that's a number I'll tell you, times the mass of the planet times the mass of whatever's orbiting it, divided by the radius between the 2 objects squared. Okay? Now this number, this letter G, is a number you're going to need to memorize. It is 6.67 times 10 to the negative 11. And there are no units. It is just an adjustment number. Now let's imagine that you are standing on the planet Earth. Here you are. Right? There you are. You're standing on the planet Earth. What force would be holding you to the Earth? Well, gravity. Well, let's back this thing up and let's look at you. Let's pan out. We're panned out. Now, here is the Earth, and you are a tiny little dot right there. You are moving in a circle The Earth is rotating, right? And you are also, here you go, boop, boop. You are one radius away from the center of the Earth. What's the radius of the Earth? Well, the radius of the Earth is 6.36 times 10 to the 6th meters, right? You probably wrote that down earlier. The mass of the Earth. Let's go back and look at our mass of the Earth. 5.98 times 10 to the 24th kilograms. So there's the mass of the Earth. 5.98 times 10 to the 24th kilograms. Now, if we're talking about me, I weigh about 75 kilograms. So here I am, 75 kilograms. And let's see what force would be pulling me down towards the Earth right here. That force right there, guess what that really is? That's my weight. Let's calculate it. F of G equals, and now I'm going to start punching in numbers. Ready? This is G. 6.67 times 10 to the negative 11th times 5.98 times 10 to the 24th times 75 kilograms divided by 6.36 times 10 to the 6th, boop, in parentheses, right? I'm waiting on the computer. Times 10 to the 6th, and don't forget the radius is squared. So let's work this problem. I want you to see the keys I'm hitting. Ready? 6.67 EE 11 negative. Okay? Times 5.98 EE 24 times 75 equals. Okay? I like to hit equals after I do the top line. And now we're going to divide it by 6.36 EE6 squared equals. And this says I weigh 739.56 newtons. Or that is, we're going to call it 739.6 newtons. And that is the force of gravity holding me down towards the Earth. That's also just my weight, right? Mr. Perkins, earlier this year when you were talking about F equals ma, and you were saying that was the same thing as W equals mg, you said, Mr. Perkins, what you said when you were talking about your weight, you said, my mass is 75 kilograms. The acceleration of gravity is 9.8 meters per second. I feel like you've already told us this number before. That's true. The force of gravity, or my weight, is equal to, let's try that, 75 times 9.8. Weird, I'm getting the exact same number. 735 newtons. And then I did it with this whole huge formula. I got 739.6 because I'm leaving off some decimals, okay? Mr. Perkins, how are these numbers the same? I'm going to show you. Now, here's Isaac Newton's gravity formula, right? Check this out. If we're talking about force, what is the formula for force? You're right. The formula for force is F equals ma. So let's replace this F of G over here. And stick with me because this is simple. And instead of writing F of G, since F is equal to ma, let's just put ma. Okay? Now, the m we're talking about here is my weight. If we're talking about how much I weigh, right? So I am m2. So if I eliminate, look, we've got an m2 on this side and an m2 over here. Boop, boop. Let's get rid of those. All right? Boom. That's gone. That's gone. Now, this is all we have left. the acceleration due to gravity is equal to the gravity constant times the mass of your planet divided by the radius of that planet squared. The mass of the planet Earth is, stick with me here, the mass of the planet Earth is 5.98 times 10 to the 24th, right, kilograms. That looks like a 20 there because of my poor handwriting. Times 10 to the 24th kilograms, right? And the radius of the planet Earth is 6.36 or 6.37, 6.3, I'm going to put 6.37 times 10. Now I'm waiting on the board again. Times 10 to the 6th meters, right? That's the radius. So if we put all these numbers together, let's see what happens. Okay? 6.67 EE11 negative, that's this number, times the mass, 5.98 EE24 equals, divided by 6.37 EE6 squared equals, holy cow, look at that number. Look at that number, 9.8. Who would have thought that the acceleration due to gravity on the planet Earth was equal to 9.8 meters per second squared? That's a brand new number. You've never heard that before. That is complete sarcasm, in case you're wondering. So, ladies and gentlemen, this is really a way that you can see that all of this is tied together, okay? The force of gravity in our new gravity formula. Gravity is equal to the mass of the planet times the mass of the object that's orbiting it divided by its radius squared. F is equal to ma, correct? And if we put this ma in for there, we would have ma equals g m over r squared. We can now eliminate the mass and the mass. And for whatever planet you have, the acceleration down, or the gravity on that planet, is going to be equal to gm over r squared. Let's do the moon. Let's do the moon. Now, one thing you might know about the moon is that if you're on the moon, you feel very light, correct? Even if you flew to a spaceship to the moon and you're going to try to sink it, you would feel very, very light. All right, so here's the moon. Now, when we see astronauts in real life walking around on the moon, it's a little bit different than this. This is what it looks like. These guys on the moon, they had on weighted boots. And it was hard for them to move because they didn't stick to the moon very well. They had less friction, actually. But the gravity's low there. Look at him airing it out right there. He's got 200 pounds worth of weight on his feet and on his back, and he can still jump like Jordan. So here are our numbers on the moon. The mass of the moon is 7.35 times 10 to the 22nd kilograms. Now, if you remember earlier in the video, I said the Earth was 5.98 times 10 to the 24th. So this is way lighter. The moon is way less massive than the Earth. And the radius of the moon is 1.77 times 10 to the 6 meters compared to the Earth, which is 6.37 times 10 to the 6 meters. So the moon is smaller and less massive. So let's figure out what the acceleration would be, acceleration due to the moon's gravity, okay? Our letter G here is a constant, all right? So we're not going to change it. And we're going to put the mass of the moon up here on the top. The mass of the moon is 7.35 times 10 to the 22nd kilograms. And the radius of the moon is 1.77 times 10 to the 6th meters. Times 10 to the 6. All right, we got to square that. So we're going to do some math. I'll show you how to punch it in once again. 6.67 EE11 negative. That's that number. Times 7.53. No, I wrote that backwards, not 53. I can't believe you didn't call me on that. Oh, that's right. This is video. 7.35. All right. Times 7.35 times, oops, excuse me, 22 equals. All right, I've made a mistake. Got to start over. I don't edit these videos, so here we go. 6.67 EE11 negative times 7.35 EE22 equals, divided by 1.77 EE6 squared equals the acceleration on the planet moon. The acceleration on the moon is 1.56 meters per second per second. So the moon's acceleration, or the moon gravity, is 1.56 meters per second per second. In other words, it's about 1/6. So if you were on the moon, you would feel like you weighed about 1/6 the moon's weight. All right? We're going to give you an assignment to figure out the acceleration due to gravity on several different planets, okay? And this is how we do it.